Okay, so the exercises for this chapter look fairly straightforward, but there is a very interesting exercise that I've asked you to do. So I want to discuss that a little bit here because I think it does give you a nice insight into what's going on. Okay, so let's take a look. What I ask you to do in the exercises is that I ask you to put H bar back into all of your computations. Okay. And so, for example, let's look at this first exercise over here. So if we had to put the H bars back, this is a loop diagram that is sitting here. So this is the loop diagram sitting over here. So putting an H bar back, I would put H bar over there. And then if you trace it back correctly, you'll find that H bar sits over there. So when we come to our matching conditions, so there would be an H bar. Well, let me put it over here. There'd be an H bar there. So if I look at my matching conditions, okay, here they are. This is where H bar would go. Okay, so there's H bar. For Z, well, Z is just equal to 1 plus order G squared, so it didn't get loop corrected. And if I was to look at the coupling constant renormalization and put the H bars back, well, the H bar would go here. We would have an H bar sitting over here, and we would have an H bar sitting over here. And really, it's just the relative H bar that I'm looking at. And I know that each loop comes with 1 power of H bar more than the tree diagram. So the one loop diagram is H bar compared to the tree diagram. Okay, now, the reason why this is very illuminating is let's just set H bar equal to 0. If we set H bar equal to 0, then we're really studying the classical theory. If we study the classical theory, what do these relations look like? Well, the first matching condition would say minus 4 factorial IG Z squared, well, Z is 1, so let me plug in the 1, is equal to minus 4 factorial I G physical. So in fact, we would learn that G is the physical coupling. Well, that's pretty interesting. And look at the second matching condition. So this would just say MP squared is equal to M squared, and then that correction is of order H bar. So we would learn that M is just the physical mass. And when we say Z is equal to 1, we're saying that the physical field is the field. So at the classical level, in fact, all of the parameters that appear inside our Lagrangian are the physical parameters. But then H bar corrections change the values of those parameters. And what are those H bar corrections? Well, for example, let's look at the physical mass relation. Where did that come from? Well, this H bar correction is really this loop sitting here. And the way that you should think about this loop here, well, what is appearing here? Something pops out of the vacuum and then it interacts with our particle, okay? So this term over here represents an interaction of our particle with the vacuum, okay? With particle-antiparticle pairs that are popping in and out of the vacuum. That's what the loop means. That's where the loop appears. Now, we discussed this diagram in quite a bit of detail in a previous lecture where I gave this interpretation. And what we're learning is when our particle moves, it's not moving through an empty region, it's moving through the quantum vacuum. And the quantum vacuum really is full of particle-antiparticle pairs that are propagating. And whenever you move through a medium, your inertia or your mass changes. So if you walk through a pool full of water, it's much harder to get you to accelerate because I don't just move you, I also have to move the water that you're interacting with. So when I pull you through the water, I'm also doing some work on the water. And here, when the particle moves, it's got this cloud of stuff from the vacuum that's surrounding it. And that changes the inertia of the particle. The same sort of idea is present here with the coupling. You see, the two particles come and interact in the first diagram. So really, they come and they interact, no problem. But in the second diagram, you see, now you're interacting sort of with something from the vacuum, which then disappears and creates the two physical particles again. So you're interacting with some stuff in the middle, okay? And this is where the quantum correction comes from. So the matching conditions really are taking into account quantum corrections, and it's due to quantum corrections that the parameters of our model are not the parameters that we measure. So I hope that gives you maybe a little bit more insight into what the matching conditions are doing. Great. Let's now move on to the next chapter and actually learn how to evaluate Feynman diagrams.